This is section 9.4 of Rosen, Discrete Mathematics and its Applications. We are talking about the closures of relations. And we will describe some closures and look at some examples, and we'll cover these other topics later. Okay, so if we have a relation on a set, that is a relation from set A to set A, it may or may not have a property, and we'll just note that property with a capital P. Could be reflexivity, symmetry, or transitivity in the case of closures. If we can find a relation S that does have that property and contains R such that S is the subset of every relation having P and containing R, S is said to be the closure of R with respect to P. That is, if S is the smallest set containing R with property P. Okay. All right, so we've talked about the concept. Let's look at it in light of the certain properties. Let's talk about a reflexive closure. Here's an example of a relation on the set A, which is the set containing 1, 2, and 3. And I say that it is not reflexive. Why not? Well, it's missing 2, 2, and 3, 3. So how could we find the closure of R with respect to the reflexive property? What if we union those two ordered pairs with R to create a new relation? It will be reflexive, and the question is it the closure? And the answer is yes. It's because all other reflexive relations on A that contain R must also contain 2, 2, and 3, 3. So we've created the smallest relation that contains R and has the property of being reflexive. All right, how about symmetry? Here's another example. Here's a relation on the set A being 1, 2, 3, and 4. And I say that this relation, all these subsets, is not symmetric. What's missing? Well, I see 1, 2, but I don't see 2, 1. And what else? I see 3, 1, but I don't see 1, 3. So it's clearly not symmetric. Now the question is, how could we find the closure of R with respect to symmetry? And here's a proposal. What if I take the union of the two elements that I noted were missing and I include 4, 1 and 1, 4? Well, that relation will be symmetric, but is it the closure? And no, it is not, because we frivolously or without cause added in these other elements. We maintain symmetry, but it's not the smallest relation that is symmetric and contains R. So the union of 2, 1, and 1, 3 with R is also symmetric. It's a proper subset of the one we just created, and it would be the symmetric closure of R. All right, now the transitive closure. Here's an example, again on the set A being 1, 2, 3, and 4. And I say that it is not transitive. What is it missing? I see a 1, 3 and a 3, 2, but I don't see a 1, 2. I see a 2, 1 and a 1, 3, but I don't see a 2, 3. Also 2, 1 and 1, 4, but I don't see a 2, 4. And what else is missing? I have 3, 2, and 2, 1, but I don't have a 3, 1. Okay, well, let's kind of go through that. How can we find a closure? Maybe we can take those missing elements and union them in. There's the things that it's missing, as we discussed. If I union those to R, will it create a transitive relation? But look, I've got 3, 1 and 1, 3, but no 3, 3. And 1, 3 and 3, 1 should also require 1, 1 to be there. 2, 3 and 3, 2 will require 2, 2 to be there. And 3, 2 and 2, 4 will require 3, 4 to be there. Yeah, so these are the elements that this would be missing in order for it to have a chance of being a transitive relation. And once we add those in, it turns out it is, but it does take a little bit more work to create a transitive closure. All right. Oh, so what do the creation of reflexive and symmetric closures have in common, but not in common with transitive closures? Well, once you have R, the reflexive and symmetric closures can be created in a single step by identifying the missing elements. On the other hand, creating a transitive closure is an iterative process. Another question, can R be its own closure with respect to P? And the answer is yes. If it already has the property P, it is its own closure with respect to P. All right, and that's the discussion of reflexive, symmetric, and transitive closures, and we'll dig in a little bit more on transitive closures later.